Hello everyone and welcome. Welcome to the latest in the series of Open STEM Talks. I'd like to welcome those of you who are here, and also I believe that we have a fairly similar number of people who are joining us online, so it's a welcome to the online audience as well. My name's Sally Jordan. I'm Professor of Physics Education and Head of the School of Physical Sciences, which is the school that Monica's in. And in a few minutes, Monica's going to talk to us on the subject 1969 and all that. Just before we start that, though, I want to quickly draw your attention to some of the other things that are going on this year to celebrate the Open University's 50th birthday. Because, of course, the significant thing for us is that 1969 was the year that the university was founded. It was the year of the Apollo landings, and I think Monica's going to talk about some other things that happened in 1969 as well. So, coming up through the autumn, next Thursday, so a week today, we've got Professor Stephen Sargent speaking here in the same series on the subject Citizen Science and the Data Avalanche. Then through the autumn, things that just come out of our school, so there's other things as well, we've got Professor Stephen Lewis talking about a blue planet to a frozen desert, exploring the environments of Venus, Earth and Mars. And then just confirmed on the 23rd of October, time still to be confirmed, but it's likely to be either 5 or 6, somewhere around there. We have Professor Jocelyn Bell-Burnell, who she's worked here for the Open University at one stage in her career, but she actually was discovered pulsars when she was a research student at Cambridge, so she's quite a famous person. She'll be doing one of the talks here. And then, still in the series, on the 6th of November, we have somebody peculiar called Sally Jordan, along with Clem Herman and Carol Morris, and we're talking about our very unconventional careers as women in STEM. So that's coming up as well. You've received flyers on your way in. We also have, we'd like to link and draw your attention to the talks that are coming up in the Institute of Physics series. Now, those are all here as well, 7:30 on the second Tuesday in the month, here. And we've got on the 8th of October, Carol Haswell, the 12th of November, Ulrich Kolb, and the 10th of December, Simone Stern-Ilio. And finally, we have two of our relatively new professors, Dave Rothery and Carol Haswell again, who are giving their inaugural lecture here again on a Tuesday, the evening of Tuesday, the 14th of November. The details are all in various places on Open University websites, but the easiest place to find all of them, and it links to all of the details, how you can book tickets and what have you, is if you look for the Open University School of Physical Sciences website in the events page there. And they're all there listed in sort of order of date. I don't want to take much more time. I just want to cover a few housekeeping items. The first is that we're not expecting a fire drill this evening. So if the alarms go off, we need to get out of here. There's an exit where you came in, there's another exit up there at the back, and if you then assemble in the car park. As I alluded, we've got a number of people joining us remotely, so join the question and answer session, which I hope we'll have at the end. We will be taking questions from our remote audience as well. Michelle will be picking those up on the computer. But if anybody in the audience has a question, can you please wait for the microphone to get to you, because otherwise the remote audience, however loud you shout, you won't get heard by the remote audience if you don't do that. And finally, at the end, we'll invite you to join us downstairs in the Beryl Cafe by where you came in for drinks and nibbles at the end of the talk. Okay, so 1969. What were you doing in 1969? Some of you weren't born. I was 12. I'm getting towards the end of my career. I remember the moon landings. I watched them on my black and white television at home. My now husband, apparently his family were posh. They had a colour television. His grandparents had a colour television. He saw them there. I don't remember anything at all about the OU, and I most certainly don't remember anything else about the things that Monica's going to speak about. So without further delay, can we welcome Professor Monica Grady, who's going to talk to us about 1969 and all that.
Thank you very much, Sally, and thank you all for coming to hear a talk about 1969 and all that. And I'm wearing, let's move it this way. I'm wearing an approximation of what I might have been wearing in 1969. You know, the old flared trousers, the mismatched hoops and stripes. If I still had the clothes that I wore in 1969 in my wardrobe, there's no way I would be able to get into them because I'm now slightly wider than I was in 1969, and I can't blame it all on childbirth. I blame it all on biscuits and red wine, but there you go. So I'm trying to be, as an Open University lecturer would also have been dressed in 1969, you know, the famous flares, the sideburns for the men, and the kipper ties. I didn't wear that. So why is my title called 1969 and all that? Well, it comes from a book that's a favourite of mine, all right, and the book is 1066 and all that. So it's an homage to this book. I don't know if many of you have read it. Somebody's put their thumbs up. A few people have read it. I really, really recommend it to you. I mean, it was horrible histories before horrible histories had been invented. And as it says in the front of the book, it says, it's a memorable history of England, comprising all the parts you can remember, including 103 good things, 5 bad kings, and 2 genuine dates. Now, it's this bit that I'm taking issue with, 2 genuine dates, because my feeling is there is a 3rd genuine date, which is, of course, 1969. Now, the problem is that this book was actually written in 1931, so they had no clue what was going to be going on in 1969. But 1969 and all that seemed to be a reasonable sort of starting point for me. So what happened in 1969 then? A few things went on. I had my 11th birthday. Aha, I'm younger than Sally. And I went to secondary school in September. That was a big deal for me, going to secondary school, having to wear a school uniform. Manchester City won the FA Cup. Obviously haven't got a room full of Manchester City fans here. Anne Jones beat Billie Jean King in the women's final at Wimbledon. Yeah, that wasn't quite the last time a British woman won Wimbledon, but there's not been very many since then. And then Murray Gell-Mann, who died earlier this year, he won the Nobel Prize for Physics for his discoveries concerning the classification of elementary particles. So this is when we learnt about quarks and so on and so forth. What else happened? Well, what happened that year was the birth of planetary sciences. That's my subject. That's what I study, the moon and Mars and meteorites and planetary sciences. And it was one of those amazing coincidence years. All sorts of things happened that year, which could have happened on a different year, but they all just happened to happen that year. And the first thing that happened was in February 1969, where 2 tons of a meteorite fell, a meteorite called Allende, because it fell over the village of Pueblito de Allende in Chihuahua in northern Mexico. I should say meteorites are named after the place where they've fallen. And it was collected and curated very, very quickly. Why? Why did the people get there so quickly? Well, actually, this village is in northern Mexico, and it's a short hop. It's about 1,000 miles, which is, you know, a long way, but a short hop by plane from Houston in Texas. And what was going on in Houston in Texas was scientists were getting ready to receive the Apollo samples. So there was a whole load of scientists there, and this news came. There's been a big meteorite fallen, and so they all sort of went across the border, or flew down to Allende, and collected loads and loads of this material. And it is an amazing material. This is a fist-sized piece that there's a picture of there. And when you break it open, you can see inside it, you can see these white things. Now, on top of this sample here that I'm pointing to, if you can see, it looks a bit like a bird dropping, all right, but it isn't a bird dropping. It's a very solid little chunk of stuff. And Allende is full of these little white, you can see the irregular, you know, there's bits here and bits here and bits here, and there's loads of them, loads and loads, and they're big in Allende. You know, this one's about 1 centimetre across in that way, and it's one of the biggest ones. Allende's also got lots of little round things in, little sort of round, like tiny, tiny little peas. And it's also got some bigger ones of those that are also up to 1 centimetre. Now, we knew a lot about these little pea-sized things, which are called chondrules, all right, which means, it's a Greek word, it means grain or seed. So this thing, Allende, it contains these large white things, all right? And they're called CAIs, calcium aluminium rich inclusions, because they're inclusions and they're rich in calcium and aluminium, all right? So that's why they're called that, so it's very logical. Now, the really exciting thing about Allende falling is there was a lot of it. And so lots of people could use it. I've got to remember, I've got to stand in front of a microphone so the online people can hear. Sorry, online people, if I wander around. So there was loads of it. And people could look at these inclusions and dissolve them up in acid and find out, well, they've got calcium and aluminium in them. What else have they got in them? And what they found is they've got very unusual oxygen in them. Now, am I talking about that? Yes, I am. Now, this is a picture of one of these inclusions that's been sliced. And this is what planetary scientists like to do with their rocks. First of all, they like to take a hammer to them and break them open so they can see what's inside. And then they'll take a thin slice and they'll polish it so it's very, very thin. So you can actually hold the slice up to the light and see light through it. It's a bit like looking through a window. And so you put that section, that slice under a microscope, and you can see all the different shapes of all the different crystals inside your rock. And these things, these inclusions, they're really irregular shape. You can see that there. It's really odd shapes. And when scientists analyse the oxygen, because rocks have got lots and lots of oxygen in, we're used to thinking about oxygen in the air, but there is oxygen in the rocks as well. And oxygen comes in 3 different sizes. One size weighs 16 units. And that's the usual, that's what we call the major bit of oxygen. And then there's 2 other bits, some weigh 17 and some weigh 18. Now, the idea at the time was that the solar nebula, which is a huge cloud of gas and dust, and the idea was it was really hot and it was turbulent and it was moving around and it was dynamic and it was really, really well mixed. Everything had all got mixed up together. Oops, not that mixed. It all got mixed up together before the sun formed, and then all the planets clustered out of this dust. But what scientists found in these things in Allende was that actually the 16 and the 17 and the 18 different types of oxygen hadn't all been mixed up at all. And there was this bit of the solar nebula, and this bit, that had these different amounts of the 16, the 17 and the 18. And this meant that actually something else had been going on in this cloud. And it was like, right, okay, so this is opening our eyes to the fact that, oh, maybe other things had been going on. Maybe when the sun was forming, it wasn't completely the same throughout the whole of this great big cloud. Anyway, that was in 1969, and 50 years later, we're still trying to find out how all these things relate to each other and what it all means, and that's what this little graph down here is. Whoops. Let's go back one. Yes, that's what this little graph down here is. Basically, it's saying, right, oh, well, that's interesting. Yeah, we still don't quite know. That's got your oxygen on it. Now, the other thing, so that's that bit there. The other thing, it says aluminium magnesium dating, all right? Now, this isn't dating like you might understand it when you swipe left or right or whatever it is you swipe when you're doing your dating app. I wouldn't know. I'm happily married and I don't need a dating app. This is dating when you find out the age of something. Now, archaeologists use carbon to date pots. You know, you get the carbon dating age. Now, we can't use that. We can't use carbon in that way in meteorites because they're far too old, far too old. We have to use something else. And we actually use aluminium. Now, you know aluminium, it's what your soft drink cans are made from, all right? But aluminium is made in stars, like all the other elements, actually, but aluminium is made in stars. And one particular type of aluminium breaks down, it decays to magnesium. So that's another element. And what was found in Allende was that we can see that aluminium, it shouldn't have been there. It should all have decayed away. Like the carbon, any carbon that was there, radioactive carbon, is decayed away. The aluminium should all have decayed away. And it hadn't. It was, the signs were still there. And what that showed was that a supernova must have exploded just before the solar system formed. And it injected a whole load of this freshly made aluminium into this big cloud, and it all got mixed up, but not completely mixed up, like I said. So Allende has shown us that not only was the cloud not hugely well mixed, but in some bits of it, it was influenced by a supernova, which had these things shot into it. And then the last thing that I want to say about Allende is about the diamonds. It's full of diamonds. You hold it in your hands and it's full of diamonds. But unfortunately, the diamonds are very, 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 very small. They're tiny. This is a cluster of those diamonds. Now, what you can't see there is that's a scale bar, which says 2 nanometers. I can't remember what it says now, it's gone. But anyway, they're very, very small. I want you to imagine, can you imagine a ruler? All right? Think of a ruler. Your ruler is divided into 30 centimetres. Imagine one of those centimetres. You can imagine a centimetre, can't you? You can see the ruler in your mind's eye. Now, zoom in on your centimetre and think of your millimetre. You've got your centimetre, it's divided into 10 millimetres. Think how big a millimetre is. Now I want you mentally divide that millimetre into 1,000,000 pieces. Can you do that? Can you imagine taking a millimetre and dividing it into a million little bits? And then take 3 of those little bits, and that's the size of one of these diamonds. So that's quite small. So a esteemed colleague of mine, many years ago, when he was analysing these, he described them. He said, if a bacterium wore an engagement ring, it would have one of these diamonds in it. All right? So there you go. So if you've got a generous lady bacterium buying a diamond ring for another gentleman bacterium, that's the sort of ring that she would be buying. Now, what's so special about these diamonds? Now, these diamonds have got a gas in them called xenon, all right? Now, xenon is a noble gas. I think lots of you will know about noble gases. Helium is a noble gas, you know, the one that's in the balloon. We get neon in the bright lights in shops, the orange and the green and stuff. Xenon is another of these noble gases. And it's in these diamonds. And in the same way that oxygen comes in different sizes, xenon comes in different sizes as well. It comes in 9 different sizes, actually. And the amount of this size relative to that size is very well known for different stars. But the xenon in these diamonds is like no xenon that comes from a star like our sun, or a star like a red giant or anything like that. It's not like any of those. And so when astronomers can't explain anything, they have 2 things they can use to sort of wipe it away. They can say, it's a black hole, all right? So if they can't explain it, it's a black hole. If a black hole isn't good enough, then they say it's a supernova. All right, and so I'm afraid, again, we're talking a supernova. Probably not the same one that produced the aluminium that I was talking about. But what we've got is we've got these tiny diamonds. So a star has exploded, and in the energy of that explosion, it makes the carbon in these tiny, tiny diamonds. And in the explosion, the xenon that's made in the explosion gets actually fired into the diamonds and sticks there. So what we've learned from Allende, from this one meteorite, is we've learned that our solar nebula isn't well mixed. It's got clumps in it. It's got aluminium in it that it shouldn't have. And it's got these diamonds that have come from a supernova. So that was just one meteorite, just one thing. Another meteorite fell that year as well, called Murchison. Now, this is much smaller than Allende. It only weighs about 4.5 kilograms, not 2,000 kilograms. And it fell in September, so we're nearly having its 50th birthday. And it fell in Murchison in Victoria, which is a lovely little town. And it fell near a farm. And it's got loads and loads and loads of organic compounds in it. Now, organic compounds are the stuff that makes coal and oil and soap and olive oil and, you know, all those sorts of things. And Murchison is full of them. And then the second thing I have to say about Murchison is it fell on a heap of manure. All right? So you might think, aha, we know where all that stuff came from. It must have come from the manure. But it didn't. It didn't. What's very special about these is that... Have I got a picture of them? Oh, no, I haven't. They're not very picturesque, aren't organic compounds. What's very special about them is they've got deuterium in them. Now, this is another of these things that comes in different sizes. So we've got hydrogen, which measures 1. And we've got deuterium, which measures 2. And there's an enormous amount of deuterium, the stuff that measures 2, in the organic molecules in this meteorite. And those molecules, they're amino acids, and they're carboxylic acids. And those acids are the building blocks of things that then can go on to become the starting materials for DNA. So what we've got in this meteorite is we've got the building blocks of life, but they've got all this deuterium in them. And the deuterium has come from interstellar space. Now, interstellar space, it's the space between the stars. So we've got the sun, our star, and we've got lots of other stars. And in between, it's not empty. There's lots of stuff there. Most of it's hydrogen. And there's lots and lots of chemical reactions that go on. And those reactions, you've got these tiny little grains, tiny, tiny little grains of rock, and the hydrogen bounces on the rock, and it might stick to the rock. And in places where it's cold, you get ice forming. And then there's lots of radiation there. and you get all these really strange reactions going on. And what those reactions do is eventually the deuterium, because there's a mixture of deuterium in with a hydrogen, gets stuck in the organic molecules on these little rocks and in the ice. And then they've got trapped somehow. They've come in to the cloud where our sun was forming. So you've got these things as well in there, these organic molecules. And in the same way that Allende has got diamonds in it, Murchison's got diamonds in as well, but it's got other things. It's got silicon carbide. Now, silicon carbide is corundum. It's emery paper. It's the stuff that you might do your nails with or sand a piece of wood down with. So it's that really, really hard stuff. And it is made in stars, and it's made in a particular type of star. It's made in stars that are coming to the end of a part of their life. And again, we know this because of the different brands of xenon that's in there, and it's very different from the stuff that's in the diamonds. And it shows that these grains have come from a star which was a red giant star. Now, the more of these meteorites we look at, the more and more of these different grains we can see, and we get different populations of them. And what we found is that we've got our pre-solar cloud, the stuff that made the sun. And there are at least 35 different stars and supernovae of different sizes that have shoved stuff into this cloud that have gradually mixed in and got themselves into the asteroids, which is where meteorites come from. So I guess I should have said that about half an hour ago, all right, right at the beginning. Meteorites come from the asteroid belt, and the asteroids orbit the sun in nice, round, circular orbits. And the sun and the asteroids, they formed a long time ago, and it's a very easy number for you to remember. 4,567 million years ago. 4,567 million years ago, plus or minus a couple of Tuesdays, all right? So 4,567 million years ago, there was this cloud, and it collapsed, and it made the sun and the planets. Some of these grains, though, that are in there, the silicon carbide and the diamonds, they're older, they're much older. They're 500,000 years older, 1 million years, 2 or 3 million years older. So these are from stars that had already gone through part of their life cycle. So it's really, really exciting. Now, I forgot, did the Allende one, did it say, oh yeah, MMG and Allende. Oh, so I was supposed to say give you an amusing anecdote about me and Allende. Can't really think of one. I have analysed a lot of Allende. Now remember, it weighs 2 tons. And one of the first experiments that I did when I was doing my PhD, I had to weigh out some of this Allende. And we'd got a piece about this big. It weighed 1 kilogram. So it weighed, no, it was 2 kilograms. So it weighed 2,000 grams, all right? And I weighed out 18 milligrams, which is a tiny amount compared to what we have. I weighed out 18 milligrams, and I put it on a little plate, and I put it in this apparatus. And what this apparatus was, it was like an oxygen plasma, and it was supposed to clean my sample. And it had a vacuum pump. And I pressed the button for the vacuum pump. And what happened to my 18 milligrams of Allende? Whoomph, straight down the pump, gone. I was mortified. This was like day 2 of my PhD. And my supervisor, Colin Pillinger, I don't know if many of you remember Colin. He was the Beagle 2 man. He was my PhD supervisor. And he just looked at me and he said, "Don't ever do that again." no, ruined on my second day. But, you know, it was fine eventually. So, MMG and Murchison, right. So, what am I going to tell you about me and Murchison? Right, well, Murchison, this was something that, this was now, I've done my PhD, all right? Yeah, Colin's forgiven me. After 3 years, he's forgiven me for losing 18 milligrams of Allende. And now I've started being a postdoctoral worker with him, so I've done my PhD. Now, we had, working in the lab, this wasn't here at the OU, this was when I was still at Cambridge, we had a sort of hierarchy. So there was Colin at the top, and then we had this level of postdoctoral workers, all right, who worked with the PhD students. And the guy who'd worked with me, Pete, you know, we worked really close together, we were really good mates and all this sort of thing. But you see, I'd now gone from being a postgraduate student. I was now a postdoc, so I regarded myself, I've gone up a level. I'm now the same as Pete, you know. So we were doing this experiment, and we'd heated up some Murchison, and we'd taken, when you heat it up, all the organics in there, if you heat it without oxygen, they turn to carbon dioxide. And what we'd done was we had decided for the first time we weren't going to heat it with oxygen. We were just going to heat it by itself to see what came off in terms of the different organics. Could we see the carboxylic acids? Could we see the amino acids? So we'd done the first bit and we'd frozen the gas down onto this pink stuff called Poropac. And then Pete had to go to the dentist. And he said, I'll be back in an hour. Just leave it until I come back. Don't touch that valve, all right? So I said, all right, okay. And then he went. And I thought, well, I'm a postdoc now. I don't have to do what he says. I can decide if I'm going to continue this experiment. So we'd frozen the gas down onto this very, very, very fine powder. And I remember it was a pale pink colour called Poropac Q. Frozen it down. And what had actually happened is all the liquid nitrogen had boiled away so that it wasn't frozen down anymore. It was still, it was at room temperature, and I hadn't realised that. And so I thought, well, what I'll do is I'll open this to the vacuum of the mass spec so that the gas can go in and the Poropac will stay frozen down. But because there was no liquid nitrogen there and I opened it to the vacuum, all the Poropac went woof, straight into the mass spectrometer, down all these tiny little capillary tubes. And I was like, oh, this is day 2 of my postdoc, actually, not even day 1, this is day 2. And it's just like, oh no. And I didn't say anything until Pete came back from the dentist. And he said, what's gone wrong? Because you could see all the dials on the mass spec, you know, they'd all, instead of all being over to this way to show they were under vacuum, they were all over that way, showing they were up at air and, you know, it was making a really strange noise and all this sort of thing. And so I told him what I'd done. And he called me something very rude, which I won't repeat because it's extremely rude. Now, Colin's office was just next door to the lab, and he heard Pete shouting at me, calling me these rude names. And so he came in to see what was going on. And Pete said, do you know what she's done? Do you know what that has done? And he told Colin, and Colin looked at me, and he said, get out of my sight, you're fired. And so I was fired on my second day. Because this pink stuff that had gone into the machine, we had to take the machine to pieces, we had to clean it, it took months, Well, I was reinstated, but, you know, so my memories of Allende and Murchison are soured a bit by my incompetence as an experimental scientist. Although I have got a bit better now, because basically I just use a microscope and it's much easier. So, what else happened then in 1969? Well, this happened. Not actually this. No, I can't take too much of that. I mean, it's just awful. So what was happening there was the Philae landed on this comet over here, which is called Churyumov-Gerasimenko. Now, Churyumov and Gerasimenko were two astronomers. Well, one of them's still alive. One sadly died the year before last. But they were two astronomers, and they were working at an observatory in what is now Kazakhstan, but in 1969 was part of the Soviet Union. And they were observing the stars, and they put out the glass plates is what they actually used to record the stars. And so on this particular night, they put out the glass plates, exposed them, took them back in the next morning, developed them, had a look to see what they could find. And they were like, what's that dot that's there? And then in the plate we exposed the day before had not been in the same place. They found something and they realised it was moving very fast, and it was on a trajectory, it was on a path that wasn't that of an asteroid. And what they'd found was a comet, and so it was named after them, Churyumov-Gerasimenko. And that was in 1969, all right? So that's amazing, because this comet then became the target for a mission that all those years later, so in 1969, I was going to grammar school, I was going to secondary school, I was going to do physics and chemistry and biology. Knew I was going to be a scientist, but I didn't know that 50 years later, or, 45 years later, because this happened in 2014, that I would be getting so excited about something that had landed on this comet. And one of the reasons why I was so excited was because I'd been involved in this mission for a long time. All right, now my husband, who is sitting in the audience, but I won't embarrass him by looking at him, he is the leader of the team that built an instrument called Ptolemy that was on that lander. And this is probably about the only time I'll boast of having slept with the chief scientist, because we've been married for 30 odd years now. But so he had designed and built this instrument, and we were in that film was taken at the operations headquarters in Germany. And Philae, we'd got the signal, it had landed. Ian wasn't there. Ian was out the back with talking to the rest of his team members who were ready and waiting. They knew that as soon as this thing came down and landed, they were going to start taking data, because his instrument was one of the first ones that was going to be switched on. And what it was going to do was it was going to sniff. It was going to take in any of the gases that were released when Philae landed on the surface of the comet. And so I got really excited, because this mission for us had started in 1993. That's when it got going, as far as we were concerned. And our instruments had been built. The rocket was launched. It had taken 10 years to get to where it was, and it landed. And it was great. Everyone was so excited. And that's why I hugged David Shuckman. And that's why now, whenever I see him, he sort of edges away from me, just in case I'm going to hug him again. And so Ian came out of the back, everybody was really happy. And he says this isn't true, but it is true. Trust me, it's true. He came and he put his arm around me, a long way, because I'm big. And he put his cheek close to mine. And I said all the things to him that the journalists had been saying to me, which is why I got so excited, you know, because it was a relief of tension. Were you worried? Are you excited? Are you happy? And he put his cheek close to mine and he whispered in my ear. He said, keep smiling, it's all gone belly up. And he says he didn't say that, but he did, because they knew that Philae had gone down and it had bounced, and they didn't know whether it was going to come back down again. Well, it did come back down again, which was good. And I was getting all sorts of messages from people texting me, you know, like, we've seen you and, you know, you looked really excited. And I got two, which I've kept. One from my niece, who's my goddaughter, and she just texted me and she said, you are the world's most embarrassing ant. And the other one was from my youngest sister, and hers was even more succinct. It just said, get a new bra. So there you go. There's you know, the supportive family. But it was a really exciting time. And Ian and his team have had fantastic results from it. Really excellent results, showing that there's organics in this sample which are related to some of the organics that are the building blocks of life. So it was really good. And it was Ian's system. No, we're not going to see that again. It was Ian's system that finally drained Philae's battery, because it couldn't. Because it landed, instead of landing like this, it landed like that. And so it couldn't get solar power to its solar cells. And so it could only work on its primary battery. It couldn't get charged up again. So Ian's got this picture which shows the voltage, and you can see it's going down and down and down and down and down. And amazingly, it was 67 volts, which is the same as 67p. Isn't that amazing? So there we go. Water. Marvellous. It is. Every drop of water that you drink has got something from a comet in it. Because we lost so much of our water when the Earth was first made, and the water's been added by asteroids and comets. So think about it. Whenever you drink water, you're drinking something from a comet and something from an asteroid. And we know a lot about meteorites and asteroids because we've got a lot of meteorites. We've collected a lot of them in Antarctica. And we've collected about 50 or 60,000 of them. I've been to Antarctica. It's really great fun. Had a wonderful time. Really, really enjoyed myself. And the question that people ask me, you know, when they say, oh, you're in Antarctica, you are on the ice. How did you go to the toilet? Quickly is the answer, all right? And I shall say no more than that. But why was I in Antarctica in 1988 collecting meteorites? How did I know that there were some there? Well, it's because some Japanese glaciologists had found 9 meteorites in a close area together. And they thought, oh, you know, it must have been one that had come down and broken. But it wasn't. They could see straight away because they were slightly different colours, because they weather different types of meteorites weather slightly differently. So they could see that actually they were different meteorites, and they'd been brought together by the ice. So you could see that actually the ice moving in Antarctica, meteorites rain down on Antarctica in the same way as they rain down on the Earth. There's no more in Antarctica than there is anywhere else. They just get preserved there, like a bag of peas in the freezer, okay? And then they move, they get carried along by the ice until they meet a mountain chain. And there's a huge mountain chain that winds its way all the way across Antarctica. And the ice carries the meteorites until they butt up against this mountain. They can't go any further, so they start to collect. And so we found huge numbers of meteorites there. And you might think, well, so what? You know, how many meteorites can a girl want? Well, you know, as many as she can get, obviously, especially if they're full of diamonds. But some of the really special ones we've got are the ones that have come from the moon and from Mars, all right? So this is a picture of a meteorite from the moon. And although it's found in Antarctica, We know it's from the moon because it's got the same type of oxygen in it that the moon has. It's got the same gases in it. It's got the same amount of iron and manganese and all these other things. It's definitely from the moon because we can compare it with the stuff that the Apollo astronauts came from. There's a piece of rock here as well. This second one, this bigger one, this is about 8 kilograms. It's about this across. That came from Mars. And so these rocks that have come from the moon and Mars, an asteroid comes down, hits the surface, makes a crater. We know there's loads of craters on the moon. You can see them, you know, just at night, you know, if you're looking out at the moon, especially if you look with a pair of binoculars, covered in craters. And Mars is the same, or it's part of Mars is. And so something has come down, made a big crater, and rocks have shot off, and some have landed on the Earth. It's okay for the moon ones. We can compare them with the Apollo rocks. But how do we know that this rock has come from Mars? Well, the secret's in these black bits here that look a bit like flaws, and they look a bit like, you know, mistakes in the rock. Well, they're where shock waves they haven't interfered with each other. They've reinforced each other, and they've shocked some of the minerals, and those minerals have melted. And as they were molten, just for an instant, they sucked in the gas that was surrounding them. And so these are frozen bits of rock, solid bits of glass, and inside them is trapped Mars's atmosphere, because we can melt the glass and we can compare it to Mars. So that's how we know. So this is something that Antarctica has brought to us. It's brought rocks from Mars to us when we've never sent any astronauts there. So Mars was also making the news in 1969, but nobody took a blind bit of notice. Mariner, one of the Mariners, Mariner 6 and Mariner 7, flew past Mars closer than any other spacecraft had been before. But it was the week after Neil Armstrong and Buzz Aldrin landed on the moon. Nobody cared. Sent back that picture, this picture here. Wow, we can see the ice caps. We've never seen Mars's ice cap before. We could tell that Mars had got an atmosphere. We didn't know that. We got some colour pictures back. Nobody cared because some men had landed on the moon or something. So that it just passed by. But fortunately, you know, lots of other things, you know, the moon is, well, take it from me, it's a bit dull compared to Mars. I mean, Mars, you know, really love Mars. Mars is exciting. Look at this, it's a delta. And this is where Mars 2020, which is a mission going in 2020, it's launching in July 2020. It's a NASA mission. So knowing the Americans, it's bound to be launched on July the 4th, all right? There's an ESA mission called ExoMars 2020, which is also launching in July. I'm not exactly sure when. But they will get to Mars in February 2021. And what ExoMars, the ESA thing, is going to do, it's got a huge drill, and it's going to drill 2 meters down to look, to see if it can find any carbon deep down that hasn't been changed by radiation from the sun on the surface. And the NASA mission is going to take some drill core and save it for another mission, which will launch in 2026, and go and collect those pieces of rock and bring them back to Earth. And they'll be coming back to Earth in 2032, which is tomorrow in terms of space exploration. So I will be a bit on the ancient side in 2032, all right? But I'm spending my time teaching people science at the Open University and helping teachers in schools teach people, because you never know, these rocks might have traces of life in them from Mars, which is really, really exciting. Right, so I'm coming to the end of my talk, but I can't do a talk without this. Right, hands up those who know what that music was. Hands up those who haven't a clue. Yes. Oh, the younger people in the audience. Right, well, the Open University, that was the opening chords of a concerto, which was composed, and they were taken to show that Open University programs were starting. Now, you've got to remember, no internet, no Netflix, no Sky, no nothing. BBC One, BBC Two, and ITV. I think it was probably just the 3 channels. And BBC Two was turned over to the Open University at night. And at the start, even video recorders hadn't been invented. And so people had to stay up if they wanted to watch their Open University programme. Now, the Open University, we got our charter in 1969. But the first explanation of what it was going to be came from this man, Harold Wilson, the leader of the Labour Party. And this is just a still, because I couldn't actually find a video of him saying it. But I'm not going to read all this out, but this is a text from his speech. But when I read it, it does bring tears to my eyes, because it is so much. This is what he was saying. Relevant also to these problems are our plans for a university of the air. I repeat again that this is not a substitute for our plans for higher education, for our plans for new universities, and for our plans for extending technological education. It's not a substitute, it's a supplement. I am going to read it all because I think it's a marvellous piece of prose. It is designed to provide an opportunity for those who, for one reason or another, have not been able to take advantage of higher education. Now to do so with all that TV and radio and the state-sponsored correspondence course and the facilities of a university for setting and marking papers and conducting examinations in awarding degrees can provide. Nor, may I say, do we envisage this merely as a means of providing scientists and technologists. I believe a properly planned University of the Air could make an immeasurable contribution to the cultural life of our country, to the enrichment of our standard of living. And that, to me, is one of the most powerful pieces of prose that I could ever read. And I've been at the Open University. I came here in 1983. I left in 91 to go to the Natural History Museum. I came back in 2005. And it makes me so proud to read this. You know, it really does make me proud, because the Open University is one of the best things that we've got. Oh, no, but I'm not going to. Well, I'll play it once more. Right, now I've got to see if I can make those slides move on. Oh no, it's going to play again. I don't want it to play again. I'm going to have to escape. I can't even escape. Aha, there we go. So that's Walton Hall on the left, and that's the Robert Hooke building where I work with Sally and Ian on the right. So, right. Summary, 1969 and all that. Founding of the Open University. University education open to all, as it still is. Momentous discoveries. Allende, chronology, the timeline of solar system formation. Murchison, extraterrestrial organic compounds. Antarctic meteorites, a treasure chest that we're still unpacking. Comet 67P, Rosetta. Mars, water, volcanoes, all sorts of stuff. Possibly even life. Anything else happen that year? Well, I can't not say anything about the moon, can I? I mean, Sally said she watched it on a black and white TV. I also watched it on a black and white TV. Now, it happened at 2 o'clock in the morning. And my memory of it was bright sunlight. So clearly I wasn't watching it at 2 o'clock in the morning. I think I must have been watching it at 6 o'clock at night on the evening news, because I remember it was so sunny we had to draw the curtains so we could see this little black and white thing. And it's like, no idea. Can't see anything. It's really blurry, not impressed. completely not impressed. I remained not impressed with the moon and lunar samples until I went to Durham to do my undergraduate degree. And there we had some of these thin sections. Remember I said that geologists polish a section until you can see through it. And they look like stained glass windows. The lunar samples were so clear and so beautiful. Rocks on Earth, they get rained on, snow, they freeze, they crack, they have, they get changed, all those sorts of things. The lunar samples, they are pure and pristine, and you look at them and their colours are so beautiful. They're like stained glass windows. And that's when I knew I wanted to study lunar samples and meteorites. And that's when I answered the advert that Colin Pillinger put out saying I need somebody to come to Cambridge and work with lunar samples. And so it's like, yes, that's what I want to do. Now that's the story which will be in my biography or my autobiography. The truth is that I would have gone to Cambridge for anything because my current boyfriend had got a job there. But, there you go. So Apollo 11, though, those rocks changed our understanding of the solar system in the same way as those other samples have. And a bit of self-promotion, why not? I've got a book called Moon, Mars, Meteorites and Me, which I hope will be coming out sometime next summer. I'm really hoping it will be coming out in time to coincide with the launch of the Mars missions. However, this afternoon I got a long letter from my agent with lots and lots and lots of comments on the manuscript, so it might not be coming out quite as soon as I hoped. Anyway, that's it. Thank you very much.